This introductory presentation will provide overarching concepts and approaches to estimating internal erosion risks. Here is the outline for this presentation. The conceptual framework for internal erosion and its phases will be discussed. There are three methods to help inform judgment when evaluating internal erosion potential failure modes: case histories, statistical methods, and analytical methods. This presentation will conclude by providing an overview of estimating probabilities of failure associated with the internal erosion potential failure modes. Conceptual framework. Internal erosion has commonly been described as seepage and piping in the literature and by practitioners, but this poorly characterizes internal erosion. All dams and levees have some seepage as the impounded water seeks paths of least resistance through the embankment and foundation and should be controlled to prevent erosion of the embankment or foundation or damage to concrete structures. Seepage becomes a concern if it is carrying material with it. Piping is actually the combination of a process of internal erosion in which a number of phases must occur and be sustained in order that a pipe develops through the embankment or foundation and allows the passage of considerable quantities of water, which may lead to a breach. The previous slide mentioned that seepage becomes a concern if it is carrying material with it. Internal erosion occurs when soil particles within an embankment or foundation are removed by seepage or leakage. Put another way, it requires a soil particle that can move and somewhere for it to go. What is the difference between seepage and leakage mentioned in the definition of internal erosion? Seepage describes flow through a porous media, for example, flow through the void space of a coarse-grained soil, whereas leakage describes concentrated flow through preferential open pathways. These open pathways or defects can occur in soil as a crack, gap, or hydraulic fracture, or in rock as an open joint, seam, fault, shear zone, bedding plane, solution feature, or other discontinuity. A lexicon or terminology has developed over the years because there have been so many issues associated with internal erosion. Many different terms are used in the literature and even in the federal agencies. This figure illustrates specific mechanisms and processes of internal erosion that have been observed in case histories and discussed in the Best Practices Manual. The term process describes more phases of internal erosion than just the initiating mechanisms. The general processes to consider are concentrated leak erosion, backward erosion piping, internal instability, suffusion or suffosion, soil contact erosion, and internal migration or stoping. Both concentrated leak erosion and soil contact erosion are forms of scour. 4 of these processes are the same as in ICOL Bulletin 164, with internal migration being added by the federal agencies. ICOL Bulletin 164 describes a stoping process as global backward erosion and considers this a form of backward erosion. However, there is no consensus on this terminology. USACE added soil in front of ICOL's term contact erosion to emphasize that this process occurs at the fine, coarse soil contact, not the soil-rock contact. Each process of internal erosion will be discussed in more detail throughout the course of this training. The hydraulic gradient influences the likelihood of initiation and in some cases progression of each of the 5 internal erosion processes. The process of internal erosion has been generally broken into 4 phases in the Best Practices Manual and ICOL Bulletin 164. Each phase of internal erosion will be discussed in more detail throughout the course of this training. Initiation involves detachment of soil particles. Continuation involves inadequate particle retention based on filtering considerations. Progression involves continuous particle transport and enlargement of the erosion pathway. Failure or breach is characterized by the sudden, rapid, and uncontrolled release of impounded water or liquid-borne solids. In this example from Fell et al. 2008, the first three phases of a case of scour initiating a potential failure mode through a zoned embankment are illustrated. A generic sequence of events was developed for evaluating potential failure modes based on the four phases of internal erosion from the previous slide. The geometric condition for initiation is an inherent weakness or flaw in an embankment or foundation, not a phase of internal erosion. It can include material susceptibility on a particle size scale and continuity on a field scale based on an understanding of the site characterization, embankment and foundation geometry, and geomorphology and geology. Initiation considers the hydraulic condition for internal erosion to start by one of the initiating mechanisms. Continuation considers the potential for an unfiltered exit and the particle retention capability of any filters or transition zones. Progression is decomposed into mechanical and hydraulic conditions. The mechanical condition considers the stability of the internal erosion pathway. This includes roofs of pipes or cracks and stable sidewalls for vertical cracks. The hydraulic condition involves continuous particle transport and enlargement of the erosion pathway. Like flaw, intervention is not a phase of internal erosion, but can arrest the potential failure mode development. If detection and intervention are unsuccessful, breach occurs. While a variety of methods are available for analyzing engineering risks, event trees have become the common approach for dam and levee safety risk assessments. An event tree is a graphical depiction of the sequence of events leading to a particular set of outcomes, in other words, breach. Event trees are used to obtain quantitative estimates of the probability of dam and levee failure and the associated consequences. The sequence of events from the previous slide are translated into the generic event tree shown. This event tree can serve as the basic building block and adapt it to project-specific conditions and potential failure modes. Events may need to be further decomposed into other necessary events to fully evaluate. There are three methods to help inform judgment when developing a list of more and less likely factors and estimating probabilities of failure for each event in the event tree. Case histories provide historical context for conditions that lead to development of internal erosion incidents and failures. Statistical methods using historical rates provide some degree of ground truth or empiricism and precedence to the evaluation, but they must be used with caution as they may not apply based on how they were developed and the sample population or inventory used. Estimating the probability of an internal erosion failure mode is very difficult and lacks deterministic approaches. However, there are several analytical methods available that can be used to inform judgment. Although they can be used to calculate probabilities, the results should be used to inform development of more and less likely factors. When estimating probabilities, the use of multiple methods is encouraged, but not all may be given equal weight or any weight, depending on project-specific factors. Each of these methods are discussed briefly in the following slides. Be objective as possible with estimates and make the best estimate, not a conservative estimate, due to the significant investments that are involved with remediation and repair. Case histories. Incidents and failure case histories provide insights to use when evaluating an existing dam or levee. The foundation conditions for 4 key dam failure and incidents from USACE and reclamation are shown on this slide. Often, the devil is in the details with respect to foundation treatment and defensive measures for the embankment. This slide shows the concentrated leakage that occurred at these dams over a 40-year period between 1949 and 1989. Only Teton Dam failed. The others were near misses or major incidents. The major lesson learned from the Worcester Dam incident is that well-constructed embankment dams can crack. Blanket drains do not provide adequate defensive measures. Chimney filters must be provided to protect embankments susceptible to cracking. For East Branch, Fontenelle, and Teton dams, a major lesson learned is that rock defects must be treated with dental concrete and slush grouting to prevent erosion into rock defects. There can be too much reliance on grouting. However, the foundation contact is paramount. The shape and geometry matter. Dams can crack, and every potential seepage or leakage exit must be filtered. A combination of susceptibilities often compounds the problem. Case histories can help teams find potential susceptibilities at a project that make it vulnerable to internal erosion. This training course will examine the incidents at Worcester Dam and East Branch Dam more closely and include some others. There are numerous case histories and compilations in the published literature. USACE, Reclamation, TVA, and FERC host a monthly case history webinar series to help share this knowledge. Statistical methods. Historical rates can provide a starting or anchoring point for probability estimation, or they can be used as a gut check for subjectively estimated probabilities. They must be used with caution to avoid misuse because of the general method in which they were developed and the inventory of dams or levees used to develop the rates. The probabilities may be more representative of several event tree probabilities like flaw, initiation, continuation, and even progression, as opposed to just initiation based on when the internal erosion process was observed or detected. In addition, teams must carefully consider whether or not the population of dams or levees used is appropriate for the specific project being evaluated. For example, embankment and foundation materials, loading history, operations, etc. Dams have failed at a rate of about 1 in 10,000 per dam year of operation, depending on the potential failure mode and age of the structure. This can form the basis for evaluating failure likelihood for a given potential failure mode that could occur under normal operating conditions. The failure rate in the University of New South Wales database after 1950 is about half the rate before 1950. Such statistics consider all dams worldwide, regardless of design and construction attention. For a specific dam, think about factors that make a potential failure mode more or less likely to occur than this historical rate. This chart shows how the failure rate for dams compared to open pit mine slopes, bridge scour, nuclear power plants, as well as common human factors such as car accidents, airplane crashes, cancer, and heart diseases. This chart was originally developed by Whitman and was most recently updated by Timchenko. Organizing case histories by location of the internal erosion pathway is useful to evaluate historical failures and incidents. But these categories are not potential failure mode descriptions. Creative thinking can be restricted if potential failure mode analysis is framed by prescribed location, which is often used in screenings. However, think about what is the greatest vulnerability for each location. For additional categories, in this list, internal erosion associated with through penetrating structures is essentially a subset of internal erosion through the embankment. Conduits through embankment dams have historically been a problem area. They are essentially built-in defects. No dam failures have occurred due to internal erosion into drains because there needs to be sufficient velocity to transport material once it gets into the drain. Drains tend to fill up with material and clog. Stoping typically occurs, leading to a relatively harmless sinkhole. Opening size limits expansion. Seepage or leakage has to find another unprotected exit point to progress. The potential failure mode can take a long time to develop, and because of that, early detection and successful intervention have stopped the internal erosion process. Foster and others in 1998 and 2000 examined failures and accidents of large embankment dams constructed between 1800 and 1986 excluding dams constructed in Japan before 1930 and in China. Approximately one-half of cases of failure in operation were due to internal erosion. The largest number of failures occurred through the embankment, and nearly one-half of these were associated with conduits or walls which penetrate the embankment. Approximately two-thirds of all failures and one-half of all accidents occurred on first filling, or in the first 5 years of reservoir operation. Nearly all failures through the embankment occurred when the reservoir level was at or near, say within 1 meter, the pool of record. The historical annual probability of failure for locations of internal erosion are shown in this table. Again, for a specific dam, think about factors that make a potential failure mode more or less likely to occur than these historical rates. This table summarizes the number of internal erosion incidents associated with levee embankments, along with the number of failures by general location of internal erosion. In the USACE levee loading and incident database, a significant internal erosion incident includes breach prior to overtopping, extensive interior flooding due to excessive seepage, flood fighting to prevent breach, or any flood damage or post-flood repair exceeding $1 million. Internal erosion failures are about equally distributed through the embankment and through the foundation. Based on the USACE levee data reviewed so far, these failure rates were established for internal erosion through the embankment and through the foundation, with and without flood fighting, as a function of levee height. These rates provide some degree of ground truth after a team has estimated the system response curve. The team can qualitatively assess the levee being evaluated as being better or worse than the typical levee in the USACE portfolio and compare the conditional probabilities of failure accordingly. Analytical methods. Participants have been provided access to the RMC Internal Erosion Suite of Microsoft Excel spreadsheets or toolboxes to support risk assessments for dam and levee safety. The training course will provide an overview and demonstration of some of these toolboxes and includes hands-on exercises using them. Because the toolbox is an Excel binary workbook and utilizes macros, you may need to enable macros before opening a file. Although not included with each toolbox, a calculation cover sheet is strongly recommended. Typical information includes some project information, description and purpose of the calculation, the assumptions for critical input parameters, a summary of the major conclusions and results, and a revision history. Each toolbox has a similar appearance and organizational structure. The first worksheet, About, provides a brief summary of the purpose of the toolbox and provides contact information for the RMC software development team. The second workshop, Terms and Conditions, contains the terms and conditions for use of the toolbox or IWR software. The third worksheet, Version History, contains the revision history. A stepwise approach is used for most calculation worksheets in which complex analysis is broken down into smaller computational steps following a logical sequence. Tabular and/or graphical summaries are the primary output of the toolboxes. Samples of the graphical outputs are shown on this slide. Graphical summaries can be helpful in visualizing and understanding the estimated performance over the full range of loading conditions as opposed to discrete numerical results, and in the development of a list of more and less likely factors. Internal erosion processes are complicated. The problem with internal erosion is that there is no well-defined physics-based model. Many of the models were developed under small-scale controlled situations in a laboratory that must be extrapolated to field conditions. The statement, "all models are wrong, but some are useful," recognizes that such models will fall short of the complexities of the geotechnical reality, but can still be of use. Models can provide a consistent basis to inform judgment, but it is imperative that the user be aware of the assumptions, boundary conditions, etc. of the model being used, and discuss conditions making the event of interest better or worse than the model. Estimating probabilities of failure. The purpose of this section is to provide an overview of the process of estimating probabilities of failure and to highlight some key considerations when making estimates. Part 1 of the Best Practices Manual should be consulted for more details. There are other training courses that provide much greater detail. The steps in the evaluation process are shown on this slide. The potential failure mode description must be decomposed into an event tree. Use the generic event trees as a starting point for consistency and adapt to project-specific scenarios. After assembling pertinent background and performance data, synthesize that data on drawings and include sketches of the failure progression. The team will need to select which loading conditions will be estimated for each node in the event tree. Not all nodes will be a function of loading. Some are just states of nature. After screening the nodes, determine what supporting analysis, if any, is needed for each node. This can include the RMC internal erosion suite of spreadsheet tools, finite element analysis, etc. Consider all supporting analyses, historical rates, and case histories to develop a list of more and less likely factors for each node and estimate the probability of each node based on the strength and totality of the evidence. Lastly, make the case for the estimate and why it makes sense. Generic event trees will be presented in this training course. It may be necessary to adapt or decompose the generic event tree to project-specific conditions. In this example of a zoned embankment, the likelihood of Zone 2 cracking is being assessed. The outcome affects both initiation, because of effective length and hydraulic gradient, as well as the exit condition. Other nodes would be the same. To assess the performance of seepage control features like tow drains, a node can be added to assess the likelihood of poor performance, which impacts the likelihood of initiation in the subsequent node. In this example, the impact of a non-woven geotextile filter wrapping a tow drain was being assessed. As part of the advanced preparation, it is important to assess which nodes of the event tree are a function of stage. In this example, the generic concentrated leak erosion event tree is shown. What nodes do you think are functions of stage? Flaw can be a function of stage if it is caused by hydraulic fracture. Initiation is always a function of stage above the base of a pipe or crack and involves assessing hydraulic shear stress. Continuation is a mechanical condition and not stage dependent. Upstream flow limitation may be stage dependent if a certain level is needed and to exceed critical shear stress for initiation. Crack filling action is mechanical conditions and are not stage dependent. Unsuccessful detection and intervention may be stage dependent, but based on different stages. Detection depends on the ability to observe the seepage or leakage. Surveillance plans are usually a function of stage, but may not activate until a high stage threshold is exceeded. Exits may become submerged with elevated tailwater. It may not matter if the exit location is obscured by vegetation or if the project is not staffed and no public is nearby. Intervention depends on the timing, but access may be cut off by the reservoir or spillway releases. Breach can be a function of stage since freeboard is an important consideration, and for small reservoirs, the reservoir level may fall below the base of a pipe. In this example, the generic backward erosion piping event tree is shown. What nodes do you think are functions of stage? A continuous path is a state of nature and is not stage dependent. The unfiltered exit can be a function of stage if it is created by heave or blowout of a cover layer. Initiation is a function of stage for vertical exit conditions, but is not a function of stage for horizontal exits where the probability of initiation equals 1, or heave or blowout of a cover layer to avoid double counting. This will be discussed in more detail in the backward erosion piping presentation. Roofing is related to mechanical conditions and is not stage dependent. Average gradient is a function of stage and is used to assess the hydraulic condition for progression. Unsuccessful detection and intervention can be a function of stage, as previously discussed. Breach can also be a function of stage, as previously discussed. A subjective probability estimate is the numerical value or range of values judged to be believable based upon the available evidence. Subjective probability estimates are typically made to represent the likelihood of each event for a potential failure mode that has been decomposed for event tree analysis. Although multiple approaches are encouraged to obtain supporting data to build the case, all final probabilities are estimated using team elicitation procedures based upon the totality and strength of evidence. Why do we use subjective probability? For many dam and levee safety applications, there is limited statistical data to work with. We are evaluating the conditional probabilities of events that have not been experienced, or whose precursor events have not yet actually occurred. In addition, we are evaluating probabilities for which there are no well-defined analytical models for computing them. Chapter A6 of the Best Practices Manual covers subjective probability and elicitation procedures. A brief review of that material is provided on the next set of slides. This leads to the question, how can I estimate a probability when I don't know? Not knowing is the essence of uncertainty. Subjective probability does not require us to know, only to honestly consider what we don't know and what we know. A subjective probability estimate is an expression of our state of knowledge at the moment. Whenever new information becomes available or the state of knowledge changes, our probability estimates may need to change as well. A verbal mapping scheme assists with making subjective probability estimates for the likelihood of each event for a potential failure mode that has been decomposed and modeled in an event tree. The mapping scheme is based primarily on experiments by Regan et al. 1989, which show that within reasonable limits, people are relatively well calibrated and consistent relative to known probabilities, provided they use words that most people would adopt on their own. Vick, 2002, summarized those results and proposed a verbal to numerical transformation convention. A key finding of the experiments was that people's ability to judge likelihood does not extend very far out on either end of the probability scale, and that most people's experience does not allow them to conceptualize likelihoods of extreme probabilities. Reclamation added one more order of magnitude to the upper and lower end of the scale to obtain the table shown on this slide. Not every node in the event tree requires an elicitation of uncertainty. For example, likelihood of holding a roof. Only estimate uncertainty when it really matters, not for the sake of estimating uncertainty. In this example, the generic concentrated leak erosion event tree is shown. The presence of a flaw is often the greatest source of uncertainty and drives the estimate absent defensive measures. As previously mentioned, initiation is a function of stage and depends on the location and dimensions of the crack, for which there will be many uncertainties. Uncertainty can be considered for unsuccessful detection and intervention, particularly at lower stages, but at higher stages, successful intervention may become very unlikely. Lastly, depending on the breach mechanism and other factors, uncertainty can be considered for breach, but in a lot of cases, if all preceding events have occurred, breach is very likely. In this example, the generic backward erosion piping event tree is shown. Similar to concentrated leak erosion, the presence of a flaw is often the greatest source of uncertainty and drives the estimate absent defensive measures. This will depend largely on the quality of the site characterization and performance history. Uncertainty is also usually considered for nodes driven by hydraulic conditions, unfiltered exit if created by heave or blowout of a covered layer, initiation, and progression. For each node in the event tree, develop likelihood factors. This is a critical step in the process because it is where the case is made for the probability estimate. Key factors that carry more significance can be shown in bold. However, the case being built for the node and the probability estimate must agree with the key factors. Generally, the evidence should point one way or the other, but a single key factor can trump multiple factors in the other column. If the probability estimate is neutral, the factors in each column are generally equally weighted. Summary. Terzaghi said the mechanics of piping defy theoretical approach. Internal erosion processes are complicated. For such a complicated process, those involved in the team elicitation should be ready to explore every clue available to guide their judgment to the less likely or more likely side of the event being considered. It is essential to use the proper balance of engineering judgment and calculations when estimating probabilities, and to understand and build the case for what most influences the estimate and why. There are indicators that will allow degree of belief estimates based on site-specific knowledge. All final probabilities are estimated using team elicitation procedures based upon the totality and strength of the evidence.